Last part of module 1, optimality of algorithms. So the most important topic we want to look at, optimality issue. So let's start with this question, D.1, minimum selection problem. First, let me give you the problem description. Problem number 3, find the minimum of an array. So it's a simple problem, but we can learn this optimality issue in this question. So given an array with n elements, find the index I such that A of I is the minimum of the array. So simple problem. Most of you can solve it immediately. To find a solution, it is not hard. But the hard part is, can you tell me if the solution is optimal or not? That's a relatively hard question. So our focus will be on the optimality of the solution. All right, first, let me give you the reference. The problem type, this one, we call the selection type. Selection problem. So last time I mentioned 3 basic types of questions in this class. Search, selection, and sort. 3 types. So we learned 1 search problem, here 1 selection problem, and we will see our first search problem at the beginning of module 2. All right. First, let me give you the selection problem. Find the kth smallest element in a given array. That k is given, but that k, so you can change the value of that k. K could be 1, 2, 3, and n. First smallest, second smallest, nth smallest. And among these selection problems, there is one special one, very important. So that's called find the median. The one in the middle, find the median, and this time k equals n over 2 seeding function. N over 2 seeding function. If n is even, just n over 2. If n is odd, n over 2, then you take the seeding function. So the one right in the middle, that's the definition of the median. So this number, kth smallest element of the array. Selection problem. All right. Today, our first one, the easiest selection problem. Kth, first smallest. All right. The reference also over here, so you can find information in the textbook. All right. So let's do the work analysis first. Let us find the solution first. Solution pretty simple, but I like to go through the whole procedure. So then we do discussion. All right. Initialization. When we start, let us initialize our variable. We take variable minimum, min, to store. So at the end, this variable should contain the minimum we need. Yeah. But at the beginning, when we start, we assign the first element to this variable for the initialization. Yeah. All right. Then the general step. So we do comparisons. For the general step, we compare this variable main with the current element. Yeah. So we scan the whole array from beginning to end. In every iteration, we compare the value in this main variable with the current element and see if the current element has the smaller value. If the current one is smaller than this main variable, then we replace it. Yeah. So we update it, replace it by another smaller value. Otherwise, if not smaller, then go to the next iteration and so on. Two students, your name?
Lokesh.
Lokesh, your name?
Brett.
Brett. Okay. All right. So I need to, write down. Yeah, just remind me before you leave the classroom. Remind me so I check your names. All right. Yeah. So the iterations, yeah, next iteration. So compare main with a of I plus 1 and so on until we finish processing all the elements in the array. Yeah. Until I equals the index of the last element. After that, at the end, then this variable should contain the minimum value of the whole array. That's the solution. The whole procedure. I think you can understand this variable should really contain the minimum value, right? Yeah. So after so many updates, yeah, finally, it must be the minimum of the whole array. Now you tell me the first question, not hard. Now you tell me, how many comparisons do we need to do in the solution? How many comparisons?
N-1.
Yeah, so what answer? Yeah, so why not here, n-1 here, any other different choices? Our first guess, we want to make it very close. Yeah. So do you think n-1 or n? Yeah, because another possible one is n. Yeah. Now you need to select which one is the right one. One is wrong, one is correct. Okay, n-1 and n. And that's the number of elements, total number of elements. Yeah. Think about this step, initialization. We assign the first element to this variable. This is an assignment operation. So we do not treat it as comparison. So for the first element, we do not do comparison. We just do an assignment. All right. After the first element, each of the remaining elements, we do one comparison. Now you can tell me what is the answer? n-1. Because we do not count the first one. First one is assignment. Okay. Yeah. So we do not count it. Yeah. We only count comparisons, number of comparisons. Yeah. So we call it basic operation. Comparison is the basic operation in this question, not assignment. Okay. Assignment also an operation, but we treat comparison as the basic operation. Okay, because the impact or the amount of time we spend on comparisons is more than the time we spend on assignment. Every iteration we need to do comparison, right? Every iteration we need to do comparison after the first one. Yeah, first, yeah. But sometimes we do assignment, sometimes we do not do assignment, right? Yeah. Here, when we update the value of this main variable, we do another assignment. But otherwise, we don't do assignment. So, you know, comparison is more important here. Yeah. All right, yeah. So we get a solution, the question, yeah. But the next question is it possible to improve the solution? The next question. Is it possible to improve it? Okay, yeah. Every time after we find a solution of a computing problem, we want to ask this question. Yeah. Yeah. All right, yeah. Here we don't know, right? We don't know if we can improve it or not. Yeah, but it's an important question to ask. All right, yeah. So the answer there are two possibilities for the answer, yes or no. Yes, then we need to try our best to improve it. If it is no, you need to explain why it is no. So that's the title of this topic, optimality question here. In other words, is the solution optimal? It's possible. This solution, it's possible it is optimal. If it is optimal, you need to convince people it is optimal. You cannot just say it's optimal. How do you convince people it is optimal? That means nobody can improve it anymore. Yeah. Yeah. So that's the end. Yeah. Yeah. No matter how hard you try, nobody can improve it. That means your solution is optimal. Here, we need to answer this question. All right. All right, so number comparisons, yeah, so we have here. All right, yeah, so then next slide. Your name? Okay, okay. Yeah, 3. All right. Yeah, came in late. Yeah. Question. Yeah. Is it possible to further improve the algorithm? Yeah. So we need to answer 2 options. Improve the algorithm. Convince people that it is already optimal. Yeah. So these two things you need to choose. Yeah. Which side you want to take. Yeah. Here, although the whole problem is easy, but if you need to improve it, you can see not easy to improve it. Think about it. Can you just reduce one comparison, n-1, if it's possible to use n-2 comparisons? n-2 for the arbitrary given array with n elements, not a special case, arbitrary given array with n elements. Even that, it's very hard. we don't know how to do it. Yeah. So we may feel there is a pretty high possibility the second case could be true. It could be optimal. So we may try to convince people it is optimal. But you need to provide convincing arguments to people. It is optimal. All right. Optimality. Here, let's look at optimality question. Hard part. Hard part. Yeah, let me explain how hard it is. So why we treat it as a hard problem. Okay, yeah. Because we need to consider all the possible algorithms to solve this minimum problem. All the possible algorithms in the world, you need to consider all the possible such algorithms. But the question, can you exhaust all those possible algorithms for solving that minimum of the array problem? Exhaust. Nobody can exhaust, right? Yeah. Nobody can exhaust all possible algorithms. Yeah. So the first thing, the hard part, yeah, because nobody can exhaust all those algorithms. Okay, yeah. Next question. If you cannot exhaust all those algorithms, how can you show our current one, our current solution is optimal? Is there some possibility we can still, even if we cannot exhaust all those algorithms, but we can still show our current solution is the optimal? Think about how hard it is. Yeah. We agree, everyone agree, we cannot exhaust all those algorithms. Okay, yeah. But we want to convince people the solution is the optimal. From the logic, is it okay from the logic? First, before we dig into it, let's look at this question from the logic. Because people make decisions based on logic frequently. Based on logic, if you cannot exhaust a group of objects, how can you say something about this whole group, right? That's the logic, okay? Yeah. Is it possible we can still convince people our current solution is optimal? This question a little hard to answer, okay? Yeah. Is it possible to convince people that the current solution is optimal? Okay? Without exhausting all those algorithms. Yeah, I couldn't write that part down because too long the sentence. I do not have that much space. Okay, yeah. So I skipped one important part without exhausting all those algorithms. Yeah. The answer is yes. Answer is yes. Answer is yes. Yeah, let me explain why the answer is yes. Without exhausting, the answer still, could be yes. Without exhausting. Yeah. So here, it looks like there is a logic hole there, right? There is a logic hole there. Yeah. But actually, we can fill that hole. Okay. We can overcome that hole, that so-called logic hole. But later you will see it's not a logic hole. Okay. Yeah. All right. So here, let me give you the main idea. Why we say yes? Because, let me complete this sentence, because we can find some common property for all those algorithms. That's the main reason we can do it. Because although we cannot exhaust all those algorithms, but we can find some common properties to cover all those, including unknown algorithms, because most of those algorithms are unknown. Unknown. Nobody knows the details of those algorithms. So unknown algorithms. But we can find a common property, even if they're unknown, but they should satisfy certain common property. Is that something good? Something important? Yeah. Yeah. But the condition is if you can find that common property. Here we need to find it. After we find this common property, then we're done. We can convince people. Yeah. Yeah. It is optimal. Yeah. So let's do that part, common property part. All right. Yeah. All right. Yeah. So here there are so many unknown algorithms, but we can still study those unknown algorithms because we can study, we can describe some special properties for those unknown algorithms. Yeah. All right. So, yeah. How do you study unknown algorithms? Yeah. You need to find, some smart way. Yeah. It's possible. Yeah. All right. Yeah. So let's do it. Yeah. Next slide. Let's do it. Okay. Yeah. All right. Question: how do we convince people that our algorithms is optimal? Yeah. We need some imagination based on our real world experience. Yeah. To solve a problem, it relies on your understanding of that problem. The better you understand that problem, the better you can solve that problem. So here we try very hard to understand this problem. Okay, yeah. So we use our real world experience to help us understand. We have a lot of real world experience. Everyone, okay? You have a lot of real world experience. So the experience is very important. Okay, yeah. So here, let's use our everyday life experience. So borrow, part of it, and try to understand this computing problem. Yeah. All right. So what kind of real-world experience? Remember, our basic operation is comparison. So we want to study, understand this comparison operation. Yeah. Can you connect this comparison concept to something in our real world experience? Is there something we do in our everyday life similar to this comparison? Yeah. Here, I like a lot of things, right? Yeah, a lot of things. Here, I just want to choose sports game. In sports game, yeah, players play each other. Can you treat as comparison? The winner beats loser, right? When we do comparison, there is a winner and a loser, right? Yeah. Think about that similarity. So in sports games, we have winner losers. Yeah. Similar to comparison case. Yeah. So let's use our experience in sports games. Yeah. Here, yeah, a match between two players, we use that, because we can imagine things well, we use that experience for our understanding on this comparison operation. Yeah. All right, yeah. So the results, after each game, yeah, we like to use less than as the winning condition. Yeah, because here our goal is finding the minimum, right? The smaller the better, right? The criteria for the minimum, the smaller the better. So we should pick the one with smaller value. Here in the sports match game, yeah. So the winner corresponds to, in our comparison, the value is smaller. Yeah. So not the other way, okay, bigger. Yeah. So we need to make that switch. The value is smaller, then we treat it's the winner of the comparison. All right. All right. Equal, tie, greater than, lose. Yeah. So we make this kind of, equivalence here. Yeah. For our understanding of the comparison. Yeah. Now, with this, we want to make the convincing argument. Yeah. Convince people this n-1 solution is optimal. Here, the goal. I need to specify the goal here. Okay. Yeah. Show that, yeah, because we need to do it. Okay. Show that the n-1 solution is optimal. Okay, yeah, so let's do the, a sequence of convincing arguments. All right, the first one, yeah, the main, we treated the final winner. Yeah, so this elements beats all the other elements. Yeah, so this player beats all other players. The final winner, this main. Okay, all right. And we interpret, that final winner. It needs to beat all the other elements in the array through comparisons, through sports matches, directly or indirectly. Here, we added this special descriptive part, directly or indirectly. So we need to understand. So what do we mean? Directly, indirect. Directly, it's easy, right? So you beat directly, okay? One player beats another player, that's easy. But indirectly, yeah, is the case like this. Yeah. What do you mean indirectly? Here, what I mean is, yeah, if A less than B, that means A beats B in our current criteria. Okay, A beats B, and B beats C. Can we say A beats C without a game, right? We do not need to play another extra game or another comparison between A and C, right? Yeah. Based on our algebra, we have a property, we have a transitivity property, right? So here in algebra, here we apply the transitivity property. Transitivity property of inequalities, transitive. Okay? Yeah. Although in our sports games, we don't have this, right? You cannot say player A beat player B, player B beats player C. Sometimes player C could beat player A, right? Yeah. So this place, so we need to make some adaptation in our understanding. Yeah. Because not comparison, not exactly as, sports games. So this place, because here we need to enforce this transitivity rule. That's the algebra rule we have to follow. Yeah. All right. So if A beats C in this way, we call it indirect winner, right? Yeah. So it's okay. Yeah. Yeah. So our main value can beat many other different values indirectly in this way. How about that? Okay, indirectly. Yeah, no problem. Yeah. All right. So that's the second statement in the sequence. Yeah. Then the next one in the sequence. Yeah. Yeah. Sorry. All right. All right. If an element loses once, it is eliminated. Is it correct? If one element loses once, only once, it cannot be the final winner, right? That's no problem. Yeah. Because the final winner cannot lose any time, any single time. Here, if one element just loses once, it must be eliminated from the final winner selection. That's no problem. Okay, yeah. So this statement also correct. All right. Each comparison can only eliminate one element. Can only eliminate, or can eliminate at most one. Can you use one comparison to eliminate two elements? After one comparison, both are eliminated. Is it possible? No, right? Yeah. Yeah. So one comparison can only eliminate, here, I need to add at the most one compare. At the most. So more precisely, at the most one element. Because at the most, that could be zero, right? One comparison, you cannot eliminate anyone because you do redundant comparison. How about that? Because that comparison is not necessary. right? Because they're pretty already eliminated. Then you do another comparison. So, you do not get more useful information. You make some redundant comparison, unnecessary. And that's possible. So that's why we say at the most one. Yeah. The best you can do, just eliminate one, not two. All right. Then the next one. Yeah, so we're closer and closer to our goal. All right, last one. Our goal, we need to eliminate n-1 elements, right? Yeah, to get a final winner, we need to eliminate total n-1 elements. So the number of comparisons we need to use at least n-1 comparisons, right? Otherwise, because one comparison you can at the most eliminate one, and we need to eliminate n-1, and you need to use at least n-1 comparisons, right? Yeah. Think about this logical reasoning. Here we need to use the strong logical reasoning here. Okay, yeah. And so at the end, from all these arguments, we can say whatever the solution it is, it must use at least n-1 comparisons. Okay, the solution number must be greater or equal to n-1. But go back to our current solution. Our current solution, we get n-1, right? Is it the best? Yeah, it is the best. Because we get n-1. That is the best. And nobody can do it better. Nobody can do better than n-1. Yeah. So the conclusion, it is optimal. How about that? Yeah, so we show people it is optimal. So nobody can do better. Okay? No matter how smart you are, you cannot do better. You cannot use n-2 comparisons to find the minimum of arbitrary given array with n elements. Yeah, so that's the optimality problem. Yeah, it's not easy. Yeah. All right, any question? All right, then let's move to the next topic, D.2, application, finding maximum and minimum. Yeah. So let us use our D.1 solution, finding the minimum. We know we can use n-1 comparisons to find the minimum. Yeah. Similarly, to find the maximum, also n-1 comparison, right? Yeah. Just a different direction. The idea, the same. Yeah. We just change the criteria. The smaller the better to the larger the better, right? So we only need to change that. Then the whole procedure almost the same. So n-1. Yeah, but in this question, we need to find both maximum and minimum. Both. Yeah. One maximum, one minimum. Oh, yeah, only one. Yeah. The maximum, the minimum. Together. Yeah. Can you use fewer comparisons? Yeah, here. So let's look at our first try. Yeah. First try, let's find the minimum first. With n-1 comparisons. Yeah, the first step. Second step, find the maximum with how many comparisons? Second step. Yeah. We already find the minimum. Yeah. We already spent n-1 comparisons to find the minimum. All right. Yeah. Now, based on that, the second step, we want to find the maximum of this array. How many comparisons do you need? Good. n-2. Yeah, not n-1. Because the minimum cannot be the maximum, right? Think about that. So the minimum is excluded from the consideration. Here you can see we use elimination method here. Okay. We eliminate the minimum. We eliminate the min in step 2. After the elimination, we can improve our solution. Yeah. So find the maximum with n-2 comparisons. So the total n-1 plus n-2 equals 2n-3. Question. Can we improve the solution? Can we do better than this? Than this 2n-3 number with a fewer number of comparisons? We want to do better. All right, yeah. Fewer, is it possible? No. Question. It is possible. It is possible. All right. Here, the idea pretty smart. Here, idea pretty smart. All right. So for the idea, I like to talk about that, this elimination method. Idea is completely about this elimination method. Okay, all right. Now, in our first try, we applied the elimination method, right? But we only eliminate one element. Is it possible we try to eliminate as many elements as possible? As many as possible. No. One, too little. You didn't take advantage of the elimination method as much as you can. If you can strengthen that elimination method part, try to eliminate more elements, then you improve your solution, right? The question is, how can you set up? You need to do some work. You need to do some setup work to make more eliminations, more element eliminations. That's the idea. Okay, yeah. Here, the comparison, you can use, sports games. Yeah, all right, yeah. So you organize some, competition. Yeah. Yeah. So those players, they play in pairs, right? Typically, and elimination round. First round, second round, elimination, right? Yeah, we have that. The first round, players are play in pairs, right? Think about that. They play in pairs. So after the first round, 1/2 of the players are eliminated. How about that scenario? After the first round, approximately 1/2 players are eliminated. Can we do similar things like that? Because we can eliminate 1/2 of the elements. How about that? Not just the one. So we can take advantage of this elimination idea more. All right. Here, let's consider. Let's group all the elements in pairs. Okay, yeah. So for convenience, first consider K is an even number. N is an even number. Yeah, because we have N elements, right? Yeah, N equals 2K. Okay, all right. N is 2K. Yeah. Can we organize our comparisons in pairs? How about that? Okay, yeah. X1, X2, oh, sorry. X2, sorry, X3, right? Yeah, 3, X4, all right, yeah. The last X2 sub 2K minus 1 is, is paired with X2K. All right, yeah. Then they play each other, okay? They do comparisons. K pairs. So we need the K comparisons. This round, K comparisons. Okay, K comparisons. All right, but after these K comparisons, for each pair, there is a winner, loser, right? Winner, loser. Winners group, losers group. How about that? Winners group, losers group. Okay, all right. For convenience, let's make this. Okay, yeah. Losers group. Okay, losers group. And the bottom half, winners group. Yeah. Yeah. Right? Yeah. All right. Now, This is the first round. When we go to this next round, yeah. How do we take advantage of that elimination idea? Yeah. We try to avoid redundant comparisons. Don't do redundant comparisons. Okay, yeah, all right. Think about in the losers group. Can you find the maximum in the losers group? Losers group. Can you find the maximum in the losers group? No, right? That means losers group. The whole group should be eliminated for consideration for the maximum. Whole losers group can be eliminated, 1/2. Similarly, for the winners group, can you find the minimum in the winners group? No. That means the whole winners group can be eliminated from consideration for the minimum. All right. So when you need to find a minimum, only do it in the losers group. When you find the maximum, only do it in the winners group. That's the way we take advantage of that elimination idea as much as we can. Okay, all right, yeah. So here, yeah. Then, to find a minimum, how many more comparisons we need to do? Find the minimum. K minus 1. K minus 1. Remember, in the losers group, we have only K elements. Okay, all right. K minus 1. All right. All right, yeah. Similarly, for the maximum, another K minus 1. Okay, yeah. So you put them together. Yeah. These 3 numbers added together. Yeah. The first time K comparison, right? Yeah. The first time K pairs, K comparisons. So K minus 1 and K minus 1. So the total is 3K minus 2. Oh, too bad. 3K minus 2. But here, because we need to go back to n in terms of n, 3n over 2 minus 2. 3n over 2 minus 2. Okay. Remember here, n is an even number. All right. For n is odd, I leave it to you. Okay. For n is odd, can you apply the similar method, but you need to modify slightly to find a solution for when n is an odd number. Because one element, you cannot make a pair, right? One element. You have, the maximum number of pairs, but the last player cannot be paired. So, it's an idle round for that player. Idle round. All right. But next time when you consider maximum, minimum, that idle player could be considered for both minimum and maximum because that player is not eliminated. That player is not eliminated. So that player can join the losers group and the winners group twice. Considered twice for the minimum and for the maximum. Then you find the answer for the odd case. Now, here, I want to save some time, so I do not go through that details. But yeah, I encourage you to try it, because if you assign you quiz questions or homework questions, I may assign you that kind of question. Okay, so try to think about it. Yeah. Okay. Yeah. All right. So we finished this topic. All right. Yeah. Here we finished. Yeah. So I skipped one slide. Yeah. D.3, the repeated cubing technique. Last time we learned the repeated squaring. So here there is a similar way to do it called the repeated cubing. Here, let me explain this one. First, let us recall the repeated squaring technique. Yeah, recall. Yeah. Last time we considered power of 2, right? Yeah. So last time we calculate the monomial x to the n. Yeah. But here n is power of 2. This case. Yeah. But this case is so special. We don't want to have this restriction. Okay. Yeah. So we want to apply this method on arbitrary positive integer n. Yeah, so first, let's consider that. Okay, all right. Yeah. So if n equals 15, it's not a power of 2. Yeah. How do we use the minimum number of comparisons? Okay, yeah, all right. Yeah, here, yeah. X squared, that's our first comparison. Okay, all right. X to the 4th, another comparison. Sorry, not comparison, multiplication. Yeah, another multiplication. Another square, all right, yeah. X to the 8th, another multiplication. And x, all right, yeah, we have to stop, yeah, because if you do another one, x to the 16th, we don't need it. Here we do not take division. Yeah, otherwise, you may argue, we move to x to the 16th, then we take division. Okay, yeah, take division. Yeah, we don't do, yeah, do the division here. Okay, yeah, we don't do the division here. All right. Yeah. Then, after 3 multiplications, you get x to the 8th. Yeah, but we know x to the 15 equals 8 plus 7. We need to get x to the 7th power. All right, but 7, how can we make that 7? Using the numbers we already have. Okay, yeah, 7. 7 equals 4 plus 2 plus 1. Okay, 4 plus 2 plus 1. So x to the 7th equals x to the 4th times x squared times x. Okay, yeah. X to the 15th equals x to the 8th times x to the 7th. Now you tell me, how many multiplications do we need? How many multiplications do we need? This we treat it as preparation, 3 multiplications. All right, 3 multiplications. Okay, yeah. Then after 3 multiplications, 1, 2, 3. Another 3, right? Another 3. So 3 plus 3 equals 6 multiplications. Or let me write, yeah, because if you feel hard to see it, let me write another way. Hopefully it's better for you to see it. Okay, x to the 15th, x to the 8th, x to the 4th, oh, x squared, x, right? Yeah, to the 4th. Okay, yeah. All right. Yeah, to get x to the 8th, we need 3 multiplications. But to get that 3 multiplications, we already have x squared, we already have x to the 4th. Yeah. So we can reuse those numbers, x squared and x to the 4th. Okay, yeah. After that, new multiplications, 1, 2, 3. So after that, another 3 multiplications. That's total 6 multiplications. Okay, yeah, 15. Yeah. All right, then let's practice another one before we move to the next topic. Another one. Yeah. So this time I'd like to take m equals 27. And try how many multiplications do we need to calculate x to the 27th power. X to the 27th power. Oh, sorry. All right. Equals x to the 16th first, right? Yeah. Times x to the 8th power, right? Oh, annoying. Then 24, okay? Only 3 left. X squared and x. All right, yeah. For x to the 16th, we need 4 comparisons. Okay, but when we get x to the 16th, we already have x squared. We already have x to the 8th. So we do not need to redo those numbers. Yeah. So the new multiplication, 1 here, 1 here, 1 here, total 3. So 4 plus 3 equals 7. That's the best we can do by repeated squaring technique. All right. Next, before we finish class today, let me use 5 minutes to show you the next slide, titled Repeated Cubing Technique. So not squaring, this time we do cube operation. The cube operation. Yeah. So what's the cube operation? x cubed equals x times x times x. We need to cube first. 1 here. So 2 multiplications here. Okay. All right. 1 cube, 2 multiplications. All right. So now x to the 27. X to the 27th. We know 27 special. 27 is 3 cubed. 3 cubed. Okay. All right. Yeah. Let's do, because repeated cubing, that means let's do another round cubing. Okay. Another round cubing, that is x to the 9th equals x cubed, x cubed, x cubed. Yeah, this round. Because x cubed can be used repeatedly, we do not need to recalculate it. Okay. So the new multiplication for second round, another 2 multiplications. Second round. All right. Then x to the 27th, another round cubing operation. This time x to the 9th times x to the 9th times x to the 9th. For the x to the 9th, we have its value. So we just put there 3 times. The new multiplication, 1 here, 2 also. The third round, also 2 multiplications. And then let's calculate the total. 2 plus 2 plus 2 equals 6. From the previous slide, how many? We did the same thing in the previous slide. 7, right? The previous slide, when we apply repeated squaring, the best we can do is 7 multiplication. But here, we reduce it from 7 to 6. It is better. Look at that. Okay. So sometimes repeated cubing can do better. Sometimes repeated squaring can do better. Yeah. Because because given arbitrary integer n, you have 2 different ways to represent. Binary representation and ternary representation, right? Binary, ternary. If you use binary, it corresponds to repeated squaring. If you use ternary, it corresponds to repeated cubing, and so on. Okay. All right. So let me stop here. Yeah.